everyone, this is Group L, and these are our members. This is the outline, which including our topic, implementation, and the result. We will show our demo in the last part. So first, our topic. We want to train a machine that is able to compose the music, and the music it generates should belong to the genre we give in the dataset. In our implementation, we train 3 models with different genres, which are classical, blue, and jazz. Our thought is that the input should be a sequence of data like pitch, note, duration, or something like that. Therefore, we try to use ion as an important part in our model. And in the implementation, we use the lstm.
Okay, this is the flowchart of our implementation. First, we'll do data preprocessing and feed the data to the lstm model. Then we can try our results by listening to the music to see if we like it or not. Okay, in data preprocessing, first we convert the MIDI file that we collected to CSV file. Then we convert the CSV file to dictionary of notes. Thirdly, we can convert the notes to characters, or you can say to strings, so that we can do one-hot encoding to those characters. And then we feed the data to the lstm model and split them into input and target according to the batch size and time step we defined. And our model structure consists of 3 layers, which are lstm layer, dropout layer, and fully connected layer. So we can train our model and save the results. Okay, to try our results, we have to define our list of notes, which will be something like this. And we have to define the music's depth so that our model can generate characters with the length that we defined and with the initial notes that we defined before. Then last, we can convert those characters back to MIDI file. This is just a reversed version of our data preprocessing, so that should be okay. And we use this package midi CSV to convert MIDI file to CSV file. And you can see the summary about this package on PyPy, or you can look at the details on its official GitHub. For example, the left-hand side is a MIDI file and the right-hand side is part of the CSV file. And in the CSV file, the first 3 lines are just some information about the music. Okay, we don't care about it. Let's just look at the red block. Here, note on C, note of C, which means that the note is starting at the time 0 and it ends at the time 512. And basically the track, they are on track 1, and the channel they are zeros. and the velocity, their initial velocity is 65, and ends at 0. Okay, they have the same format. So the most important three parts are just the begin and the ending notation, the time and the beginning time and the ending time, and the number of the notes. 69 according to the table means A4. So those three parts are the most important. Okay, and here's the full table of the notes. Then we convert the CSV file to string. For example, again, let's look at the red block. Here's the notes and the quarter rest. So we have to specify the notes in the CSV file, right? And the number 1024 means that's the duration of the note, which can be calculated by subtracting the 6144 with 5120, so we get 1024. And because there is a quarter rest, we can know that the next note's arrival time is at 2048. So this number means the next characters, the next note's arrival time, and 79 means G5 according to the table. Okay, then you can see that the string basically is composed of just some alphabets and some numbers and hyphen. Totally, there are 20 characters, 20 kinds of characters. So after one hot encoding, the dimension of each vector should be 20, and it will be something like this. Okay, and here's our model structure. We name our model to be CHARNN, which means character-based recurrent neural network. And there are 3 layers: lstm, dropout, and fully connected layer. That's just as mentioned. And we can see that the number 20 is the input size, and we convert it to 128 in the hidden layer. Okay, and the number 4 means that the number of hidden layers in lstm, and we set the dropout probability to be 0.2, which means that at the end of each hidden layer, the parameters are randomly drop out with the probability 0.2. Then we add an additional dropout layer after lstm with probability 0.2 again. Last, we have to convert the dimension back to 20. So we add a fully connected layer at the end. Okay, in case that you guys don't know RNN or lstm, I just briefly introduce. RNN stands for recurrent neural network, and lstm means long short-term memory. And there are many types of RNN: one-to-one, one-to-many, many-to-one, many-to-many, and another version of many-to-many. So basically, lstm is quite similar to RNN, but inside each neuron there are some different computation method. Yeah, a little bit more complicated. And here's an example of RNN. The time step is defined to be 4. So the model can only read 4 characters at one time. Okay, so if we want the model to learn the word hello, then given HELL, it should output ELLO. That's what we aim for. Let's get the picture on the right hand side. The input characters are HELL, and the input size, the dimension of the input should be 4, and the dimension of the hidden units, they are converted to 3, and unless they are converted back to 4. So in our case, the input dimension, the input size is 20, and the hidden size is 128. That's our case. And as I mentioned before, the computation inside each neuron is more complicated, but we don't need to know how the vectors are computed. We just need to know that there are 2 vectors, which are the arrow on the upper side and the arrow on the lower side. They are the vectors C and H. We have to initially set those vectors, and by default the number will be 0. They are 0 vectors by default if we don't specify them. Okay, so our model will finally look like this. The red row means the inputs, and the green rows are the hidden layers, and the blue row means the output layer. And let's see, in the code we set an lstm layer, which will be the red to the green part. So we convert the input size from 20 to 128, which means the red one is of the size 20, and the green one, the dimension is 128, and the length of the uh, the neurons is called time step, or you can say sequence length. That should be fine. And dropout layer, or you can draw an additional dropout layer, but that should be fine. You just need to know that dropout layer means you just randomly set the parameters to be 0 with some specific probability that you defined. Okay, and fully connected layer converts the dimension from 128 back to 20. And there are four rows of hidden layers, which is defined here. So that should be no problem. Okay. And this is the cross entropy loss of one of our models. We can see that as our training process goes on, the cross entropy loss is really decreasing, so the model is really learning. Okay.
Now we're gonna to demonstrate the music we generate.